This is the first lecture from Chapter 5. It's dealing with the gas laws. I think you guys will enjoy the gas laws. The math in it is fairly straightforward and it's fairly simple. It's pretty much Algebra 1. Generally, you'll have like an inequality, an equation, where you will know, you'll have a series of variables. You'll know all the variables with the exception of one. And it generally just involves rearranging and solving for that one unknown. So overall, pretty easy chapter. The first thing, though, before we get into this, we need to know some background information. And this lesson is going to teach you about units of pressure and units of temperature. Okay, the first thing we need to talk about is pressure. What is pressure? Well, scientifically speaking, pressure is simply the force per unit of area. And so you'll notice here in a couple of diagrams I have got somebody standing on this first one, a bed of nails, and on this diagram we have someone about to stand on a nail. All right, and I think you guys kind of can predict the outcome of this scenario. All right, and so we look at this first picture, you're like, okay, how can this person stand on this bed of nails? Well, if you think about it, force per unit of area. Okay, you can stand on things like beds of nails and not be harmed, because the fact is that, notice they're standing on hundreds and hundreds of nails. So each individual nail head, has very, very little force pushing down on it, very little weight. The weight is spread out evenly over the entire the foot. Whereas, in this second scenario, where you've only got one nail, well, that's not going to end as happily. The guy's probably going to end up impaling his foot on that nail, because you have a lot of pressure, because you have, the force, the force of gravity pulling the body weight down upon that small area, that single nail head. It's going to go through. Now, believe it or not, the atmosphere, the air around us, exerts pressure upon the surface of the earth. There is constantly pressure of the atmosphere pushing down upon you. It's been around you every moment of your life. You don't really realize it because you're always surrounded by, roughly a fairly similar amount of atmospheric pressure. There are certain little fluctuations in the pressure and so forth, but it maintains a fairly constant amount. And you'll notice here in this picture, imagine you have a column of air that is 1 square meter, so you have a meter by a meter, and notice that column extends from the Earth's surface all the way up into the upper atmosphere. Well, that amount of air has mass, and as the Earth's gravity pulls it down towards the Earth, that mass is sitting upon you. I don't know, exactly atmospheric pressure in like pounds per square meter, but I do know in like pounds per square inch. So if you took like a 1 inch square by a 1 inch square, like on your arm, believe it or not, there's 14.7 pounds sitting on top of that square inch of the surface of your body. Now, you might think, oh, that makes me heavier. Well, not really, because it is exerted to everything in the room. So, it's exerted onto your desk and onto your books and onto the floor. And also, any measuring device where you'd be taking a measurement of your weight, like the scale. The scale is also is experiencing that same exertion of 14.7 pounds for every square inch on it. And it's been calibrated out. So, it is not contributing to your weight. Another thing you should be aware of is that, the atmosphere is not of equal density, throughout the entire atmosphere. And you'll notice here that it says that roughly 80% of the total mass of the atmosphere, so all the matter, all the particles, all the gases that make up the Earth's atmosphere, exist in the lowest region, called the troposphere, and that's the portion of the atmosphere where we live. It's the bottom. The troposphere, it's roughly 17 kilometers thick. That's at the equator. If you get up by the poles, it's much thinner. It's only roughly about 7 kilometers thick at the poles. But anyway, the thing that you should find kind of interesting, though, is that the actual atmosphere itself extends to roughly 1,000 kilometers above the Earth's surface. So, I mean, obviously, a vast majority of the stuff is smashed in just the very, very bottom of the atmosphere. And you'll notice in this diagram, in the upper atmosphere, not a lot of particles up there, very low pressure. If you get down towards the bottom where we live, it's very, very dense and very high pressure. You have the weight of all that air sitting on top of it, smashing them together, making them dense. A lot of matter per unit of volume. And that's, consider it this way. Think about, air is, believe it or not, it's a fluid, just like water. It flows. You guys may have experienced like swimming in a swimming pool. And as you dive down into the deep end of the pool, the pressure gets much greater because you have a lot more water sitting on top of you than if you just dived down in a very shallow end of the pool. So you can think of us, as really living at the bottom of the sea of air. That is our atmosphere. A device used to actually measure the pressure that the atmosphere exerts on the surface of the Earth, it's called a barometer. And a barometer can be a very simple device. This is an example of, one of the very first barometers that was invented by Evangelista Torricelli. He was an Italian scientist, and he came up with this device used to measure the pressure of the atmosphere. Okay, so you'll notice it's pretty simple. It contains basically a dish. He used mercury, so it's just an open dish, a dish open to the atmosphere. And then he had this glass tube that he placed in this dish. So basically what he did is he took this glass tube, completely filled with mercury, placed his thumb over the edge and inverted it into the dish of mercury and removed his thumb. The mercury level then fell some distance, and then at some point it stops. You guys have probably done this before. You might have noticed when you're washing dishes or even, messing around with like a soda straw, that you can have a column of liquid suspended above the surface of a liquid. So like say you take a cup, in your sink and you fill it with water, you can invert the cup and lift the cup up out of the water. And as long as you keep the mouth of the glass below the surface of the water in the sink, the water stays up in the glass. And the same thing is actually occurring here. Notice it has fallen some distance, however, and notice that up here now you have what is known as a vacuum. A vacuum is simply an area of space that contains no matter. Okay, so there's no air in here, there's no mercury, there's no water, there's nothing. It's just empty space. It is a vacuum. If you do this with water, you're going to find that you're not going to have this vacuum forming because the atmosphere will hold a column of water up into the air 30-some feet. So you would need a very long tube in order to experience this with water. But with mercury, it's a heck of a lot denser than water. You do get this area where it drops. Okay, so what's holding this column of mercury up here? Well, the answer, it's the downward pressure of the atmosphere. So as the air pushes down on the surface of this mercury, it's holding this mercury up in this tube. All right, and so we're going to go on the next slide. You're going to learn about some common units of pressure, but one of them is millimeters of mercury, and it's basically just what it sounds like. It is a measure in the unit of millimeters. It's just a length of how high a column of mercury will be supported by the atmosphere. So it'll measure from the surface of the mercury to however far up it is in the tube you read it. That is the atmospheric pressure. Here are some of the more common units of barometric pressure. The one we just kind of discussed was millimeters of mercury. It's abbreviated mmHg. Like I said, mercury is very commonly used just because of the fact it's really, really dense. Therefore, you can make a barometer that is fairly small and portable. For example, if you look to the right of the smartboard, there hanging on the wall. You have that wooden bracket with a glass tube. That's a barometer. That's a mercury barometer. Notice it's only roughly 3 feet in length. That makes it fairly portable. If you had a water barometer, they have one at UNO. If you go down there to the Durham Science Building, University of Nebraska at Omaha, right there in the lobby, they've got a barometer that's made of water. In order to read that, you have to go up to the 3rd floor because it's 30-some feet into the air where the atmosphere will support a column of water. The next unit you will see is called a torr, T-O-R-R. This one is actually the exact same thing as a millimeter of mercury. 1 millimeter of mercury is 1 torr. All right, it's a little confusing, but here's the deal. Torr is named once again after the guy who really discovered or invented the barometer, Torricelli, and so posthumously, so after his death, it was renamed the torr in honor of him. So a torr and a millimeter of mercury, the exact same thing. The next one is atmospheres. It's abbreviated ATM. Another common one are called kilopascals. Notice it's a lowercase k, capital P, lowercase a, kilopascals. Kilo just means 1,000, so it's 1,000 pascals. And then another one, we won't really use this a lot, but you hear it just in everyday life just because we live in America, and a lot of times, like if you're looking at, pressure of car tires and things, they'll be rated in something called pounds per square inch, or PSI. So that one we won't use as much, but it's probably the one you've heard the most of. And because there are different units of pressure, we need some method, to be able to convert from one unit of pressure to the other, and we're going to use dimensional analysis to do this. Here are some common equivalent units of pressure. So 1 atmosphere is the same as 760 millimeters of mercury. That's a pretty important one. That's one we'll use quite a bit. And then, like I mentioned on the previous slide, 1 millimeter mercury is 1 torr. So if you just can remember those two things, they're identical, they're the same. The next one's also fairly important to know. 1 atmosphere is 101.325 kilopascals. And then the last one, 1 atmosphere is 14.7 psi, or pounds per square inch. That one, not as important, but it's just kind of, I don't know, you may see it maybe on a quest assignment or something, so it's just good to know. But out of these 4, this one's probably going to be the most common one. We'll use this one as well. This one really isn't a conversion because they're the same thing. But if you get these 2 down and you realize that's the same thing, you're probably good to go. Let's work a sample problem out together, doing some dimensional analysis, converting units of pressure. Alright, I have a sealed container, and it has a gas pressure of 1260 torr. I want to calculate that pressure in atmospheres. Well, as always, let's start with what we know. We know 1260 torr. Alright, well, let's think of a conversion factor. Well, I know that I don't know necessarily between torrs and atmospheres, but if you recall, I know that a torr and a millimeter of mercury are the same thing, and I know that 1 atmosphere is 760 millimeters of mercury. Therefore, 1 atmosphere is also 760 torr. So, since I know that relationship, and I want to get rid of torr, I need to put the torr on bottom. And how many? 760. So 760 torr is 1 atmosphere. The torrs cancel. I grab my calculator. 1260 times 1 divided by 760. And I get a number with a string of decimals. However, I should be limited to 3 sig figs because this number only has 3 sig figs. Only the 1, 2, and the 6 are significant. The 0 is not. There is not a decimal. So I must round my answer to 3 sig figs. It should be 1.66 atmospheres. Okay, now I want you to try one there in the silence of your heart at your desk. Okay, let's say we have a scuba tank that has a pressure of 3.3 atmospheres. I want you to calculate the internal pressure of that tank in kilopascals. So I'll give you guys a minute here. Go ahead and pause the video and see what you come up with. Okay, well, let's take a look here. As always, we should probably start with what we know. So we know that we have 3.3 atmospheres of pressure in this scuba tank. And I want to convert this to kilopascals. Well, looking back at my conversions, I know that 1 atmosphere is 101.325 kilopascals. So atmospheres cancel atmospheres. I'm going to go ahead and get out my calculator. 3.3 times 101.325 and divide that by 1. Notice my answer can only have 2 significant figures because 3.3 atmospheres. The answer must be 330 kilopascals. And do not put a decimal after that. So 330 kPa. Okay, the next fundamental idea that we have to kind of focus on for the gas law chapter deals with temperature. Temperature is basically a measurement of the average kinetic energy of particles in a substance. Kinetic energy just is basically that energy of motion. So basically it's just measuring how fast particles are moving. You see this word heat. A lot of people think like heat and temperature are the same thing. They are not. They are totally different. Heat is not temperature. Heat is basically a measure of the amount of energy a substance contains and its ability to transfer that energy to other substances. So I like to give you this classic example of heat versus temperature. Okay, you'll notice here in these 2 diagrams, these 2 pictures I have there, I have a burning matchstick and then I have a bunch of logs on fire there in the fireplace. Now basically those 2 things are both wood that is burning, correct? Believe it or not, the temperature of the fire on that match head and the fire coming off those logs is the same. Now think about it. It makes sense. It's like you don't want to stick your finger, in the flame on the match. You definitely don't want to stick your fingers in the flames coming off those logs, right? So the temperature of the flame coming off that match and the flames coming off those logs is equal. However, the heat is dramatically different. Okay, let's say it's a cold winter night here in Nebraska. The power is out, but your family's got a wood-burning fireplace, so you guys can stay warm. Are you just going to light a single match and throw it in the fireplace and all huddle around? Well, no, that doesn't make sense. It's going to burn out fairly quickly, and it's not going to be able to transfer a lot of heat energy into you. However, if you burn a bunch of logs, they will make you warm. They will heat up the room because they have a lot more heat energy contained within the larger mass of wood that is present. So that'll give you some idea of the difference between heat and temperature. Sitting here before you are 4 devices that are used to measure temperature. These are thermometers. A thermometer is a very simple device. These are the most simplest forms of a thermometer. Basically, it's just an evacuated glass tube, so it's a glass tube that all the air has been removed, and basically it'll have some liquid in the bottom. If it's a mercury thermometer, you'll see kind of a silvery looking liquid. If you see like a red or a blue colored liquid inside them, that's going to be an alcohol thermometer. Okay, so the mercury thermometers are a lot more accurate. However, mercury is fairly poisonous. It's a neurotoxin and it's a cumulative poison. So it's something that, they used to use very commonly in thermometers, but it's not as widely used today just because of, health risks and, putting it in a glass tube. Glass isn't, exactly the most impervious material. It's fairly easy to break. So not super common anymore, but you still do see them. So if you ever see a thermometer with a silvery colored material in it, that's mercury. Be careful not to drop it. Okay? So anyway, here are 4 thermometers. Let's say that these thermometers are submerged in a liquid, all right? And let's say that it's submerged in, let's say some ice water, okay? And let's say the mercury that's down here in the base of all these, so here's, well, this isn't mercury, let's say this is just alcohol. Whatever, all right? Let's say it's submerged in some ice water and it rises up, it goes whoop. And notice all 4 thermometers are the exact same dimensions. They have the same materials, and so they're going to raise up the same amount. All right? And in this case, let's say, these temperature scales, believe it or not, ladies, are just man-made. They're just made up. The ice water has no concept of temperature. Temperature is a scale or a system that is invented by people. Notice we have 4 temperature scales here. The first one you're going to be very familiar with, Fahrenheit, degrees Fahrenheit. The next one is degrees Celsius. You've probably heard of Celsius, but you're not real familiar with it probably. The third one is Kelvin, and then the last one is called degrees Hacker. And so let's say we have some ice water here, and you know that water freezes at, in Fahrenheit, 32 degrees Fahrenheit. Okay? Celsius, the Celsius temperature at which water freezes is 0. Kelvin, this is going to be 273. And let's see, for degrees Hacker, let's say it is 2. Okay? All right, so we have our thermometers and we've submerged them in ice water. Now let's take them and put them in a boiling water bath. Okay, the liquid level is going to go up, whoop, 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 went up on all of them. Okay? And so now we have another baseline or another constant point. So we have the freezing point of water. Now we're going to look at the boiling point of water in these 4 temperature scales. Okay, let's see, Fahrenheit, you know that water boils at 212 degrees Fahrenheit. Celsius, I don't know if you're aware of this or not, but water boils at 100 degrees Celsius. Kelvin, it boils at 373 Kelvin, and let's see, Hacker, it's 4. Okay, so there's our 4 thermometers, and we've got 4 different scales. Now, which scale's right, which scale's wrong? Well, they're all right, and each one of them, kind of has advantages and disadvantages. Just right off the bat, let's just look at like the degrees Hacker. The degrees Hacker one, not super useful. Not super useful because, you're ranging from, you think of, between 2 degrees water's freezing and 4 degrees water's boiling. And so, what would room temperature be? All temperatures would be somewhere around 3 that, we exist or we find in everyday life. So degrees Hacker, not a super useful one. I just made that up just to show you that, these other ones were just made up by people as well. Fahrenheit, it's one we commonly use, but it's not commonly used throughout the world. Celsius is by far the more commonly used temperature scale. One nice thing you'll see between the Celsius and the Kelvin scale, the number of degrees between freezing and boiling on each one of these is 100. Okay, so between the freezing point and the boiling point of water, there are 100 degrees or 100 units between those. So that these two share that in common. Fahrenheit, there's actually 180 between there. We don't really use Fahrenheit at all, so don't really worry about that. But it's kind of significant the fact that those two, Celsius and Kelvin, the degree sizes are equal. That makes conversions between them very simple. One other thing I want to mention very quickly while we're on here, notice there is no degrees Kelvin. Temperature in Kelvin is just listed Kelvin. There is no degree symbol. It's just whatever the temperature, Kelvin. It's important to note that in the gas law chapter and subsequently other following chapters that the temperature scale that we very often are going to use in chemistry is going to be the Kelvin scale. The reason for this, Kelvin has no negative numbers. The lowest possible temperature is 0 Kelvin. It's also known as absolute zero. This is the temperature at which all molecular motion stops. Basically, you cannot have less motion than no motion. So 0 Kelvin is the lowest temperature that can be recorded. It's kind of important that we use Kelvin and why. In some of our math calculations, if you end up using negative temperatures, like if you were to use Fahrenheit or Celsius, which we all know definitely have a negative region, you're going to end up with negative volumes, in our answer. How can you have negative volumes or negative pressures? Is that an area in the universe where a gas should be, but there isn't? Well, no. I mean, that's just a vacuum. It's just empty space. There is no such thing as negative volume. You either have volume or you don't. And that's why we must use Kelvin. One last detail and we'll get you out of here. Some temperature conversions. If I'm converting Celsius temperatures to Kelvin, basically all you do is you take the temperature in Celsius, you add 273 to it. That will give you your Kelvin temperature. That's probably the more common conversion we're going to be doing here. But then the reverse one you can do very easily. It's just rearranging and solving for the other one. If I have Kelvin and I want to calculate Celsius, you simply take the Kelvin temperature and subtract 273. That will give you your Celsius temperature.